Okay, so I'll go to the first question without any more delay. The first order correction to the energy of the nth state due to a time independent perturbation V is given by. Okay, so let's look at the options. N, B, N, modulus of the expectation value of V. Okay, you've got 0 and you've got N, B, N squared. So I think you've kind of like done your perturbation theory, time dependent as well as time independent. And here they're kind of like talking about time independent, and this formula is quite easy to remember. Okay, so I think you might have learned this with a H prime. Okay, so it would have been like H prime. So basically you would have something like psi n 0. Okay, it's the expectation value of the perturbing potential in the unperturbed state. Okay, these are called your unperturbed states, and this is basically the perturbing potential. Okay, so yeah, I think this should be fairly easy to remember. Okay, so in the other one where you have your second order correction, you basically have this mod squared, you end up having a k coming up, and then you divide it by E n 0 minus E n k. Okay, so I think this is how it is. Okay, so the thing is, I think you would have done it right now, like very recently, perturbation theory and time dependent, time independent. So I think it's best to like go and remember those formulas, write them down in a sheet of paper and keep it, like I said for the other things that you had, or for the canonical transformations that you had, you could probably just write them down in a sheet and then keep it and read them before you go to bed so that you don't forget them. Okay, so because deriving these takes, like, I think even when you did your, when you attended the classes, it would have taken like 2 to 3 hours, and it's going to take quite a bit of time. So this is the first order correction to the energy in the expectation value of the perturbation in the unperturbed state. And this is what you have, okay, the first order correction, E1. Okay, so like I said, this is your perturbing potential, and this is the unperturbed state. Okay, so this should have been state, not stated. Okay, so typos coming up. Okay, so this is basically a second order correction, and this is what you would have had. Okay, so let's move on to the next one. Okay, so this is pretty easy. I think you should know this. Okay, I think there are lots of questions on these Bose-Einstein, Fermi-Dirac, and Maxwell-Boltzmann statistics coming up. So I think it's best to like look at the BSc version of all those things. Okay, so Pauli's exclusion principle is valid only for bosons, fermions, photons, excitons. So basically what you have is, when you're talking about Pauli's exclusion principle, you know that they cannot be more than two in one state, right? So there can only be one of a kind in that particular state. So if there are 2 electrons in one state, the one has to be spin up and another one has to be spin down. You can't have both spin up, right? So those kind of things come under this Pauli's exclusion principle. And what are those kind of things? Those kind of things are basically your fermions. Okay, those kind of things are basically your fermions. So let's look at this a little bit. The Pauli's exclusion principle describes the behavior of all fermion particles with half integral spin. Okay, and your boson with integer spin. And then you basically have your fermions, which are basically your quarks, electrons, and neutrinos. Okay, so all those kinds of things come under your fermions. So that's just something that you know, just to kind of like recall whatever we've done before. Okay, so this is kind of like tricky. Okay, so listen a little carefully when you're going to be just listen a little more carefully when we're doing this question. Okay, so the expectation value R of the position of the electron in the ground state of a hydrogen atom is dash times the radius of the first Bohr orbit. So now we know that basically this is called your Bohr's radius, right? So you have something called the A naught, And let's look at our options that we have here. Okay, so is it 0.5 times, or is it 1.0 times, or is it 1.5 times, or 2.0 times? Okay, the Bohr radius. Okay, so they're asking you for the expectation value. So when they're asking you for the expectation value, okay, it's not just taking an average. Okay, it's not as simple as that. You just don't do 1/2 into A naught. It's not like that. So when you're doing the expectation values, basically you're going to be having to do a lot of integration. Okay, so you basically take up doing psi. Okay, so if I'm going to say this is basically the hydrogen atom wave function, okay, let me just put it as psi h for now, and I will explain it to you in detail. Okay, and then you would have psi, this would be star, okay, and you would have the value r coming in between, and then you have dr, and you would go on to calculate the expectation value for this. Now, that would take you an incredible amount of time, because this wave function has a lot of components to it. Okay, so your hydrogen wave function has your r, you have an exponential e power some terms and all that coming up. So I think you would have kind of like combined two wave functions in this topic that you've done, where you have to kind of like evaluate the ground state of your helium atom. Okay, so you would have taken psi 1 0 0, and then you would have another psi 1 0 0 with an r1 vector and r2 vector coming up. Okay, so if you recall what you've very recently done, this would come up. So this is basically combining two hydrogenic states. So that would take you an enormous amount of time to do this. Okay, so what I'd suggest is by heart the expectation values for any value of psi NLM. Okay, so I've kind of like put out a table. Okay, so basically I think you would have evaluated the expectation value of 1 by r, 1 by r squared, 1 by r cubed, and I think if you would have kind of like read your Griffiths, I think there's a footnote in that part which talks about something called the Feynman-Hellman theorem, and this theorem was something that Feynman did while he was doing his BS. So he actually proved that part, and there was some other person who also did it, some German person who did it, but I think Feynman got most of the credit for that part, because he did it as a very young student while doing his BS. Okay, so yeah, let's look into this. Okay, so this is basically, I just want to show you a pictographic representation before I show you all the equations. Okay, so I don't know if it's very clearly visible, but there is a division sign here. Okay, so it's A naught dp divided by dr. Okay, and you see that it's not just the average of your A naught, but rather 3/2 of n A naught. Okay, so A naught is basically what? Your Bohr radius. So this can be evaluated by what I said before. You can kind of like find those expectation values from there. But what I'd suggest you do is basically by heart these expectation values, and I'm sure you would have done this one, okay, and this one and this one. Okay, so I think you would have had something like, okay, so they put the A naught here, but you would have done something like psi NLM 1 divided by r psi NLM. You would have written it this way. Okay, if SB ma'am, I think in her notes she kind of like did it this way, I think. Okay, so you would have 1 divided by A naught n squared. Okay, so this is how they would have written it. Now, how do you find out something like this? So they've told you that you need to find it for a hydrogen atom in the question, right? So when we read the question, we found out that we need to find out this for a hydrogen atom. So let me just write down the hydrogen atom wave function. So I will write psi NLM can be written as psi 100. Okay, so 100. That's your hydrogen atom wave function. So then you know that you have n, which is 1. Okay, n which is 1, L which is 0, and M which is 0. Okay, so now let's move on to this part. Okay, so now what do you want? You want the expectation, you don't want the expectation value of 1 by r or any of these. What you want is the expectation value of r. Okay, so you want this. Okay, so in that situation you basically have 3n square minus L into L plus 1 divided by 2. So L is 0 for you, so this part goes away, it becomes 0. And then you have 3 into, what do you have here? You basically have 1 squared divided by 2. That's going to give you 3/2. Okay, so you have an r divided by A naught that comes here. So when you're calculating the expectation value of r, this A naught comes here. So that's why you have 3 by 2 A naught, which should give you 1.5 A naught. And let me go back to that point where you have the question. So basically you have option C coming up, okay? So I don't know if it's quite clear, but if you have any questions, get back to me on this, okay? So write this down in a sheet of paper and kind of like stick it. I keep saying this, but I don't think anybody is like implementing it. So yeah, I'd probably check up on people once I'm done with this or something like that. Okay, so just write these down in a sheet of paper and remember it, because these are very useful tools, and I'm sure you will really regret it if they ask you for the expectation value of 1 by r square for a hydrogen atom, and then you will be like, oh, I should have just remembered that table. Then I could have done it very easily and quickly. Okay, so rather than computing your expectation value using an integral and then doing, you know, integrating by parts and doing all that mess, you can just do this. Okay, so this too, I want you to be a little careful, because when we've kind of like done the transition probabilities for this, okay, we did this in the first semester, we were just asked to write the amplitude square divided by the incoming wave amplitude square. I mean, the outgoing wave amplitude square divided by the incoming wave amplitude square. So when you're looking at your potential barrier, I suggest you kind of like go through this intense derivation, okay, where you have to kind of like, well, take those amplitudes and kind of like approximate and reduce it down, okay? So this question basically deals with the kind of like intricacies of that derivation, not, you know, like how we did it, but a little more deeper into what we've kind of like done. Okay, so the tunneling through a potential barrier increases if the height and the width of the barrier are increased, the height and width of the barrier are reduced, the height is increased and the width is reduced, and height is reduced and width is increased. Okay, so let's just look at this. Okay, so what is your quantum tunneling? Basically, the particle has a lesser amount of energy than your height of the barrier potential. We've discussed this in the previous paper, and it can just pass through that way. Okay, so without having to cross that potential. Okay, so this is extensively used in making nano devices. Okay, so basically what's going to happen here is you will kind of like see in the formula, once we kind of like get to there, that the tunneling is kind of reduced when the barrier height and the width are increased. Okay, so when the barrier height is increased, it is more difficult for me to pass through. Okay, when the width is increased, it's more difficult for me to pass through. So even if you like logically think about it, okay, so if I have to pass through a longer distance, it's going to take more effort for me. Okay, and if I have to kind of like climb a higher level, it's going to be more difficult for me. Okay, so I would prefer it to be narrow and shorter. Okay, so I think that's the way you should look at it. Okay, logically, like how you deal with it in real life. Okay, so that you can remember that point rather than having to by heart that formula. But I'll give you that kind of description too. Okay, so this is the approximate version of the your transmission coefficient that you have. Okay, so you basically have TLE. So L is basically the length of your potential and E is the energy. Okay, so U naught is basically the value of the potential that you're climbing over. E is basically the energy of your particle that we're talking about. Okay, so what you're supposed to be looking at is this value, U naught. Okay, and you're supposed to be looking at your L. Okay, so these are the two things that you're supposed to be looking at. So if my L increases, let's just look at it one quantity at a time. Okay, so let me just look at L first. Okay, so if my L increases, what's going to happen? E to the power of minus, let's say it's blowing off to some infinity or something. So if e to the power of minus infinity. Okay, so what's going to happen here? You basically end up having some minimal value, right? So then the transmission kind of like decreases. Okay, next let's look at your U. Let's say U is also blowing up to some real big value that you have. Okay, so if your U is blowing up, your T2 decreases. Okay, so that's basically what we're talking about here. But in the question, what have they asked for? Okay, So let's go back and look at what they've asked for in our question. They've basically said the tunneling through a potential barrier increases. So we're looking at when does the probability of transmission increase? So they're saying that when your height and width of the barrier are reduced, it obviously increases. So if you look at it logically too, you can come up with that answer if you do not remember the formula. But even if you know the formula, you can, like assure yourself that it's the correct value. Okay. So this is pretty simple. Okay, you know this formula. You know that the energy that you have in a one-dimensional square well of infinite potential is basically going to be proportional to n square. Okay, so E is proportional to n square. They've kind of given you the ground state of the particle. Okay, so that's going to be E naught. Okay, they've given you this. So you have E sub n is proportional to something like, let's just say, equal to E square E naught. So you can automatically just do n squared here. So 4, 3 squared here, so 9, and multiply it with this 10. So you end up getting 40 MeV for your second state. And what else do you get? You get 90 MeV for your X state. So that's really simple to do. Okay, so these are the options that you have. It's option B. Okay, so one of the things that I'd like to kind of point out to you is this. Okay, so when you're looking at a system, something like your harmonic oscillator, what's going to happen is basically you're going to start with your n equal to 0, 1, 2, and so on. Okay. Okay, so in this case where you have your infinite square well that we're talking about, we are basically going to start with the n equal to 1, 2, 3. Okay, so you have to be very careful about this. Okay, you can never have your ground state energy as 0. Okay, your ground state has to be some certain value that you need. Okay, here in this case your ground state isn't 0, even though your n is 0, because you basically have something like n plus 1 by 2 h cross omega. Okay, so you have to keep that in mind. One is starting with 0 and the other one is starting with 1. Okay, so let's just look at this formula: n square pi square h cross square divided by 2ml square. So if you know this formula, you can even look at your length. Okay, so in the other case the length was constant, so it really didn't matter, and the variation was only in your state number. Okay, so this is something that I really want you to note. One starts with this one particular. Okay, this square well starts with your n equal to 1, whereas your harmonic potential starts with your n equal to 0. Okay. Okay, so let's look at this question. A system in an external field will be in equilibrium when the following physical parameters of each component of the system is constant throughout is. Okay, so this is not very correctly framed. Okay, it's not a very correctly framed question. Also, it does not tell you what kind of equilibrium they're talking about. So it's not a very good question to be dealing with, but I will try to kind of tell you about how much you can learn from this question. Okay. So they did give the option as B, but I think this wasn't challenged at all during that time. Okay. So a system in an external field will be in equilibrium if the following physical parameters of each component of the system is constant throughout that. Okay. So what are those parameters which have to be constant? So basically they've given temperature and chemical potential. Okay. So now they haven't talked about what kind of equilibrium. Okay. So they've just said external field and it has to be in equilibrium. Are they talking about thermal equilibrium? Are they talking about mechanical equilibrium? Are they talking about some other kind of equilibrium? So let's just look at that. Okay, so I will tell you about the different types of equilibrium and each of the parameters that are constant when you need that kind of an equilibrium. Okay, so the various types of equilibriums are achieved as follows. Okay, so two systems are in thermal equilibrium and the temperatures are the same. Okay, so this you know. Okay, thermal equilibrium, temperatures have to be the same. When you're talking about mechanical equilibrium, we're basically talking about pressures. Okay, so two systems have to be in mechanical equilibrium when their pressures are the same. Okay, and the other case is basically diffusive equilibrium when their chemical potentials are the same. So I think here it's not, if they're talking about the entire thing, like all the three, then you might have to add temperature, pressure, and chemical potential. But in this case, they've just kind of given us temperature and chemical potential, and I don't think it's just it has to be, I feel like it has to be in mechanical equilibrium, because they're kind of like talking about an electric field acting on this. So yeah, I think the question could have been challenged if it was like properly kind of like, you know, like thought about. Okay, so it's not a very good question. I confirmed this with the teacher, so don't have to worry about that. Okay. Okay, so let's look at this. Okay, so this is quite easy. Okay, so these are quite simple. Okay, in quantum statistics, the volume of phase cells is h being your Planck's constant. You automatically know it's h cube. You don't even have to compute it. Okay, so I'll just go through it anyway. Okay, so you basically start finding out the volume of your phase space from using this Heisenberg's uncertainty principle, right? What is that? Basically, the minimum of your uncertainty in the product of your uncertainty in position and momentum. The minimum of that should be h. Okay, so you can't go any less than h. That's what it means. Okay, so you basically have something like this coming up. So the minimum minimum volume that your phase space can have, okay, would be something like h cube. Okay, so no volume can, the basic idea is that if you have something like, say, h cube, okay, so this is your volume h cube. Let's just draw it this way, although it's not possible to draw it this way. Okay, so if this is the volume that you have, okay, you cannot, if it is less than h cube, okay, so basically if your volume is less than h cube, the phase space volume, you basically cannot fit anything into it. That's what it kind of like means. Okay, so it's this, and this is how you represent your phase space, d tau. Okay, so d tau is equal to h cube. Therefore, the uncertainty in your phase, because of this uncertainty principle, you basically have your phase space volume element. Okay, the coordinates of a particle can only be specified within an element of phase space volume h cube and no less. Okay, so it cannot go below h cube. Okay, so let's look at this. Okay, so this is, I think this, I think you should automatically kind of like pick the answer once you see the options. Okay, so we kind of like discussed about these different things. Once you do one paper, it kind of like, the next set of papers are like kind of like revision. Okay, so the collection of large number of essential independent systems having the same energy E, volume V, and number of particles N are called what? Ensemble, grand canonical ensemble, and microcanonical ensemble. So let's just revise what was your microcanonical ensemble. So microcanonical ensemble basically means isolated system. Grand canonical ensemble means you have a transmission of energy, but no transmission of particles. Did I say grand canonical? I'm not very certain. I meant canonical, okay? So canonical ensemble basically means you have transmission of energy, but no transmission of particles. When you look at your grand canonical ensemble, you basically have both, okay? So ensemble is basically a collection of systems, the collection of your different possibilities that your system can be in. That's basically what your ensemble means. Not just collection of systems, but the collection of different possibilities that one system can be in. Okay, so basically, let's take a fan. Okay, so I think this idea isn't like put out very well. So if you take a fan, and if it has sort of like different colored blades, okay, so I don't know if this is very nice, but yeah, okay, so this is your fan. Okay, and if it has different colored blades, you can kind of like turn it around. Okay, so if you turn it around and say, okay, this is one position that you have, then the next one is red. Okay, so you have another position, and then you have something like this. Okay, so you have another position. So this kind of like keeps rotating, and then you have different kinds of state that your system can be in. Okay, so the system that you're talking about is just one system. But when you're talking about an ensemble, you're basically talking about a collection of states that your system can be in. Okay, so it can be infinite number of states that your system can be in, and maybe some of the states are impossible in real life. Okay, so that's what you're talking about. Okay, so the microcanonical ensemble basically describes your isolated system. Okay, a canonical system is basically in contact with a heat bath, so that means there is energy exchange in your canonical system. Your grand canonical, basically you have a heat and particle bath. So there's both energy exchange as well as mass exchange. Okay, so this is basically what your ensemble means. So I think I've like covered it all. I don't know why this is given as option A. Okay, so I think I kind of like messed it up. It's supposed to be option D, because let's just read this part. Okay, so they've said the collection of large number of essential independent systems having same energy, volume V, and number of particles N. Okay, so in this you have same energy, volume, same number of particles, then you end up having your microcanonical ensemble. So I just want to correct this. I should probably edit it and then give it to you. This is not A. Okay, this is not A. This is D. Okay. So let's move on to the next one. Okay. The partition function Q of a system that contains large number n of molecules freely moving inside a volume V is related to a single partition function Q as, okay? So let's look at this, okay? So let's just draw this picture because you can get easily confused, okay? So you're talking about a big system that you have here, okay? The partition function is Q. And then you're talking about a molecule, okay? Here, okay, so you've got a set of molecules, about n molecules, okay, about n molecules that you have, and the partition function of that is Q. Okay, so how are they related to each other is what we're talking about. Okay, so let's look at this. Okay, so your initial instinct is just go to this. Okay, so you initially I think you might remember the canonical the partition function for the canonical system. So you basically end up writing Z is equal to summation of I, and then you write e to the power of minus beta EI. Okay, and then what do? You say, okay, fine, I'm going to have n number of such partition functions, and there is a summation here. So I think maybe it should be something like Z1 plus Z2. Okay, and then you end up writing something like, let's say it as NQ. Okay, so this is wrong. Okay, so this is not how you're supposed to be going about it. Okay, they're saying, how does the partition function Q of the system that has several sub particles inside it, okay, going to be related to each other? Okay, so for that, I will go through this. There is a derivation so that I can help you understand this a little bit more better. Okay, so basically it's going to be Q is equal to Q power n. Okay, so when you start off with this, you basically say, okay, fine, I have something like this. Okay, so this is the energy of one molecule that I have. Okay, and then there is energy of another molecule that I have. Okay, and then what I'm going to be doing is, okay, so let's just look at this. Okay, so the total collection of your n independent molecules is the sum of the energies of the molecules. Okay, therefore the total energy of a system of state I will be, you can split it up. Okay, so you remember that you wrote Z is equal to e to the power of minus beta EI. Okay, and you summed it all up. Okay, so that EI is basically this. Okay, so you're summing it up with all the energies of your individual molecules. So basically when you're saying epsilon I1, you mean energy of the first molecule. This is referring to the energy of the second molecule. This is referring to the energy of the nth molecule. Okay, and they're all going to be same. Okay, so now, okay, so let's move on to this. Okay, so let's look at the canonical partition function that you have. So Q is equal to summation of I. You know that it's e to the power of minus beta capital EI. So once you substitute all of that, you end up getting something like this. Okay, and this summation can be split over all of this. So you can basically write it as products. Okay, you can write it this way, as product of one term, then the product of the next term, then you have a product of this one, and then you go on. So each of these individual molecules which have same energy, okay, each of these individual molecules which have same energy, okay, you're basically going to have to write the partition function as Q for this, Q for this, and Q for this, and so on. Okay, so that means you have to multiply Q n times. Okay, so this is very simple. Okay, You're not adding your partition functions like this, okay? You're going to split it up and you're going to be writing it in terms of the energies of the molecules that you have inside the system. And all of those energies are the same, okay? All of them give you the same partition function. And then you have to multiply it so many number of times, n times, as many number of times as the number of molecules in your system. So you end up getting your q power n, okay? So it is not q is equal to n times q, but rather q is equal to q power n, because you're talking about the subsystems inside a system, okay? You're not talking about different energies, okay? So it's different energies means it's a whole different thing. You're talking about something which has the same energy, but is there inside an entire system, okay? So, okay, so another thing that I want to tell you is about distinguishable and indistinguishable particles, because if you look at this, they really haven't told you that these n molecules that you have are distinguishable or indistinguishable, okay? So they haven't told you that, because if you end up having an n factorial somewhere here, you're going to be for a toss, okay? So if you, because they haven't told you if it's distinguishable or indistinguishable, I will just go on to elaborate on this a little bit more, okay? So they said for distinguishable particles, it's going to be q is equal to q power n, okay? So that is fine. Now what happens if you have indistinguishable molecules, okay? So you have to divide it by n factorial so that you don't count those partition functions multiple number of times. And I'm sure you might have seen this technique a couple of places where you divide it by n factorial, because you do not know what kind of, you do not know how to segregate or differentiate these different things that you have, okay? So you would have done it in probability theory mostly. Let's move on to this. There are about 5 more questions that we have, okay? So which of the following statements is not true? Okay, so this is pretty simple. These are your Bose-Einstein statistics, fermions, Fermi-Dirac, all those kinds of things. So I feel like there are a lot of questions that have been asked from this section, okay? So even in the previous paper, we had a couple of them. So let's just go through this. Bose-Einstein statistics deals with distinguishable particles. Fermions obey Pauli's exclusion principle. So let's just look at this. Okay, so this, you know, it's true. Okay, you automatically know that it's true. Maxwell-Boltzmann statistics deals with distinguishable particles. And Fermi-Dirac statistics deals with indistinguishable particles. So this, you know, is true. Now let's look at this. Okay, so Maxwell-Boltzmann statistics is basically the first statistics that you have. Okay, and it does deal with distinguishable particles. Okay, but Bose-Einstein statistics deals with indistinguishable particles. Fermi-Dirac statistics deals with indistinguishable particles. Okay, so this is the one that's false. Okay, so this is basically option A. Let's just look at this kind of like this table that we have. Okay, so basically you have Maxwell-Boltzmann statistics, which gives you distinguishable particles. Bose-Einstein, Fermi-Dirac, indistinguishable. In this Maxwell-Boltzmann statistics, unlimited number of particles can occupy one quantum state. Okay, so it's basically the ideal gas molecules case. In your Bose-Einstein statistics, you have unlimited number of particles per quantum state. So basically it's your photons and your phonons that come into that picture. And in your Fermi-Dirac statistics, there is only one particle per quantum state, okay, because of your Pauli's exclusion principle, and that basically means your electrons and protons. Okay, so here you have distinguishable, the last two are like indistinguishable, and in the first two you basically have unlimited number of particles per quantum state, and the last one you can have only one particle per quantum state. Okay, so let's move on. It's quite simple. That was quite simple. Okay, so they're basically asking for the Boltzmann relation here, and I'm sure you would have like it memorized already. Okay, so yeah, so let's just look at all the options. Okay, so Boltzmann relation is between your entropy and the probability. Basically, you would have written this as big omega instead of your W. Okay, so they've kind of like put it like W, and S is equal to K ln omega. So I don't know if you know about this, but Boltzmann kind of like actually committed suicide. Okay, he kind of yeah, he kind of like had a lot of theories and a lot of thing to put out, and a lot of his colleagues never took it the right way. Okay, so everybody kind of like opposed him with his theories and things like that, and he was suffering with a lot of mental illness for a lot of time, and one fine day, like when he was on vacation with his family, he kind of like committed suicide. So it's really sad. I mean, like if you kind of like read about his life. So yeah, I think this famous equation that is here is kind of like engraved in his tombstone. Okay, so S is equal to K B ln of omega. Okay, so it was omega, I think. That was, I don't know. Okay, so it's basically called the Boltzmann-Planck equation. Okay, so it relates basically your entropy and the number of microstates. So when you're talking about the probability, basically you're saying the number of microstates corresponding to a particular macro state. So macro state is basically temperature, pressure, things like that. And microstates is what is the actual state of the system individually, okay? Corresponding to that particular temperature, okay? So I think you know all this. This is quite common. Okay, so basically it's telling you how, okay, it's basically giving you a relationship between the entropy of a system and how you can arrange your atoms and molecules, okay? So when you're looking at arrangement of atoms and molecules, you're basically looking at a microstate, okay, that the system can be in. And there are several different possible states that your system can be in. Okay, so this is his tombstone, and on top of it, it's kind of like written S is equal to K log W. Okay, so yeah, so that's that. You might have seen that picture a lot of times. Okay, so let's look at this. With regard to the Fermi-Dirac distribution function f of E, where E refers to energy, which of the following is true at room temperature? Okay, so let's just look at this. So f of E has a value of 1/2. Okay, that's your probability function. Okay, it has a value of 1/2, where EF is your Fermi energy. EF is a step function. States with E less than EF are filled completely, and EF is large and tends to infinity as E decreases much below EF. Okay, so one thing that you know about a probability distribution function is that it's always between 0 and 1. Okay, it's always between 0 and 1. So you can rule this out immediately. Okay, the last one, f of E is large and tends to infinity, is completely ridiculous because it's a probability distribution function and it cannot tend to infinity. Okay, so it's always between 0 and 1. Let's look at the next one. Okay, so they've said at room temperature, which of the following is true at room temperature? Okay, so let's look at this. They say that the states with E less than EF are completely filled. So when you're looking at such a situation, it's basically something that's very close to your Kelvin. Okay, so it's not very much close to your room temperature, right? It's something close to your 0 Kelvin. So you can rule that out immediately. Also, when do you have your Fermi-Dirac distribution as a step function? It is when your temperature is equal to 0 Kelvin that you have a function like this. Okay, so you basically have a step function like that. Okay, that is only when you have your system being at 0 Kelvin. So it's not room temperature, definitely. Okay, now what you kind of realize is as the temperature kind of like, you know, goes lower, I mean, goes higher and higher compared to your 0 Kelvin, it kind of like goes this way. And I think you might have done this even in your BSc. So it basically goes this way and ends up kind of like reaching this 0.5% probability. Okay, so 0.5 probability compared to the one which it was at T is equal to 0 Kelvin. Okay, so let's just look at all these functions that we have. So f of E is your Fermi-Dirac distribution. So I think this is a very nice way to kind of like write it down. Okay, the formula is basically you're kind of like not just listing whatever properties down, but actually directing it to them. Okay, so the probability that the particle will have, okay, the probability that a particle with energy E will have is given by this. Okay, so here what you have is your Fermi energy. Sorry, here what you have is your Fermi energy, and then you have all this. Okay, so you can just go through this. This is something that you know and you've done and you've repeatedly kind of like memorized it. If it's Fermi-Dirac, it's going to be this way. If it is Maxwell-Boltzmann, it's going to be this with a negative sign. If it's your Boltzmann, it's just going to be without the one and things like that. Okay, so let's look at this. So T is equal to 0 is basically the temperature at 0 Kelvin, and as your temperature increases, the probability kind of like increases along with that. So one thing that I want to like show you is like kind of like look at the formula and tell you that, okay, fine, we're going to have probability like say 1/2. Okay, so how do you do that? So I want to kind of like make this go to infinity, okay, and the energy to be going to 0. So what you're basically going to get is something like this. So you're going to get 1 divided by 1. Okay, so I will just say there's no E. Okay, there will just be something like this. Okay, and this I'm going to like kind of like turn it to infinity. So you end up getting e to the power of minus 0, which is going to give you 1. Okay, so e to the power of 0 is going to give you 1, and then you already have another 1 there. So you basically have 1 divided by 2 coming up. So that's your 0.5% probability. So even if the temperature goes up to infinity, okay, so which is, they say room temperature, so it's probably going to be a little more higher than 0.5, but it can never go lower than 0.5, even if it throws off to infinity. Okay, so let's move on to the next one. Okay, so this is something that I kind of want to like discuss a little carefully. Okay, so for the temperature less than TB, okay, so TB is basically your Bose-Einstein condensate temperature. Okay, so it's called the Bose temperature here. The system is in a gas phase, condensed phase, mixture of gas and condensed phase, and neither gas nor condensed phase. So we have to be a little more careful when we are talking about this, because there are two things that we have to look at. Okay, so one is at 0 Kelvin, basically you end up getting a condensed Bose-Einstein condensate. Okay, I will just put it as BEC. Okay, at 0 temperature, it's completely a Bose-Einstein condensate. But then there is something called a critical temperature at which the gas starts to condense. Okay, so let me just put that as TC. Okay, and that is your Bose-Einstein condensate temperature. Okay, so in this temperature range, basically you're going to end up having both gas plus condensate. Okay, and then above that, you're basically going to have just gas. Okay, so this is how it looks. And when they say your T is less than TB, okay, it basically is stating that it's a mixture of gas and condensed phase. Okay, so it's option C. Let's just kind of like go through it in detail, and I'll show you how your Bose-Einstein temperature looks. Okay, so basically, what do you mean by a Bose-Einstein condensate? It's basically, it's sometimes called the fifth state of matter. Okay, so it's basically formed when you have a gas of bosons at low density cooled to very low temperatures, which is close to about your absolute zero. And then a large fraction of your bosons occupy the large quantum state. And basically all these properties come up. You can go through that. Okay, we kind of like discussed it last time, I think. Okay, and yeah, okay, so this is basically your BEC temperature. Okay, so it's called the critical temperature, and I think that's what they should be meaning by Bose temperature. Okay, so yeah, this is basically your Raman zeta function. This is your density. This is your Boltzmann constant, mass of the particle, and so on and so forth. Okay, so all this. Okay, so now let's move on to the next one. The width of the depletion layer of a junction. So this is electronics question. Okay, you should probably go and read through this, because I am doubtful whether most people do this part. Okay, it is a very popular question, but I'm doubtful people remember it. Okay, so the width of the depletion region of a junction is independent of the applied voltage, decreases with light doping, increases under reverse bias, increases with heavy doping. So basically your doping is referring to the concentrations of your acceptor and donor. Okay, the applied voltage is basically referring to your V here, and there is also another relation where you just have your VB, which is the barrier potential, and that is nothing related to the applied voltage. Okay, so it's basically the barrier potential that's there around, in and around the depletion region. Okay, from one place to another place. Okay, so let's just look at this. Okay, so the depletion region is basically a insulating region. Okay, so where you have your charge carriers basically diffused away. Okay, so there are no carriers, basically your depletion region is basically what the word kind of says. It's depleted of charges, okay? A region depleted of charges. So the only thing that's there is basically your ionized donor and acceptor impurities. And this is when you don't have an applied potential. So this is quite, I think many people know this, okay? So for your formula width of this is a formula where you have your width of depletion when there is no applied potential. So your V here is 0 and WD is equal to root of 2 epsilon divided by E into 1 divided by Na plus 1 divided by Nd, which is your donor and acceptor concentration. Okay, so let's move on to this one. The formula for width of your depletion region when there is an applied voltage V with your bias is basically, okay, so you have a with bias applied here, so you basically have a V naught minus V coming up here, okay? So that's when you have to kind of like be careful, okay? So what happens when you have a reverse bias? So when you have a reverse bias, it's negative, right? So when you subtract it from your V naught, you're basically going to end up getting a positive quantity here. So your width basically increases when you have reverse bias. And when you have forward bias, your W kind of decreases. So when you're looking at the concentrations that you have, I mean, when you're looking at this question, basically, what they're kind of like saying is the width of the depletion layer of a junction. What happens? So basically, it kind of, let's look at the formula again. So you have a dependence of your voltage here, and you also have a dependence on your acceptor and donor concentrations here. Okay, so it's coming to option C, which means that it increases under reverse bias because why? You have your V minus of, let's say V naught minus of minus V. So then you end up getting a big positive quantity in the numerator and hence it increases, okay? So let's move on to the last question we have. Okay, so this is quite easy. Okay, so you really don't have to know much about electronics. All you need to know is the photon is energy formula, and you can kind of like do this. Okay, so the band gap of a semiconductor material used to make an LED is about 1.43 electron volt. What will be the minimum wavelength of the radiation emitted by this LED? So all you have to do is, you don't have to look at any fancy formula for this. You basically do E is equal to h nu, E is equal to hc divided by lambda, lambda is equal to hc divided by E. It's very funny like how simple things are, okay? So you just have to look at the band gap energy kind of like related to wavelength and then calculate it out. Okay, so this is quite simple. Okay, so I think I'll kind of like edit this up. Okay, so basically I think some was a 6 and something like a 5. Okay, so I'll do that correction and I'll propose the corrected PPT. Okay, so yeah, so this is what you have. It's option B. Okay, so after you substitute the values of H and C, you end up getting option B. Okay, so that's it for today.